Thank you very much. Good afternoon, everyone. First, I would like to thank the organizers for this very nice conference and the opportunity. I came from Budapest, Hungary, and with our research group, we developed the MRCC program package. And today I would like to talk about how can we reduce the basis set incompleteness error in quantum chemical calculations. The CCSD parentheses T method is considered as the gold standard in electronic structure theory community. The total energy using a finite one electron basis set denoted by B can be split into as a sum of the Hartree-Fock energy and the CC correlation energy. Of course, the applied method has an error compared to the exact results, but this is completely out of scope of this talk. And today I will focus only the error of the basis set, and this can be measured with respect to the complete basis set limit. Inspecting by inspecting a very simple chemical reaction, we can conclude that the BSI error with increasing basis set size, it is decreased. However, at the same time, the basis function used for the calculations and the work log times steeply increase. To reach the chemical accuracy, which is 1 kilocalorie per mole, at least the augmented 6 Z basis sets are required, and these calculations are very demanding and not feasible to extend this method to large systems. So the question is how can we reduce the basis set incompleteness error? The most trivial answer is the explicitly correlated methods, but they are rather complex in terms of derivations, implementations, and computational requirements. A few years ago, a very effective and robust approach was developed by Julien Toulouse and his coworker called density-based basis set correction. And in this case, the correlation energy at the CBS limit is approximated with this formula, where this guy is the so-called complementary DFT correlation energy functional, and it depends on the Hartree-Fock density and of course the basis set applied. I don't have too much time to go into the details, but this contribution accounts for the missing short-range correlation effects arising due to the incompleteness of the one electron basis set. And this functional is basically a short-range DFT correlation and energy functional, which depends on a range separation function. So this is not a range separation parameter, this is a range separation function which characterizes the incompleteness of the basis set in space. The key point is the calculation of this quantity, which scales with the 4th power of the system size. So in this method, the total energy is obtained as a sum of the Hartree-Fock energy, the CC correlation energy, this DFT correction, which improves the correlation energy, and the so-called CAPS correction, which decreases the basis set incompleteness error for the Hartree-Fock method. And a few words about the performance. We calculated different thermochemical quantities for a well-known benchmark set, and these values were compared with the complete basis set limit. For the atomization energies, we can see that drastic error reduction is achieved with the double zeta basis sets, while significant improvements are realized for the triple zeta basis sets. Similar results are obtained for the reaction energies. The improvements are somewhat modest, but still the results are obtained with the errors are obtained with the corrected method are lower compared to the standard CCSD parentheses T method. So now let's aim for large-scale applications. Our research group has a long history of developing local correlation methods. In this case, the correlation energy is decomposed as a sum of the contributions of the individual occupied molecular orbitals denoted by I. If we localize these orbitals, then a compact restricted domain can be formed around each occupied orbitals, and the corresponding equations are only solved within these domains. It means that many wave function parameters can be eliminated and linear scaling can be achieved for the CC part. So consequently, for extended systems containing hundreds or thousands of atoms, the CAPS correction and the density-based basis set correction would be the bottleneck in these calculations. But the good news is that the contribution of this range separation function can also be split up, and the contributions can be evaluated or calculated only within these domains. To this end, we implemented the corresponding equations in our very efficient and good local CCSD parentheses T framework. For benchmark calculations, we found that using normal cutoff parameters or domain construction parameters, the additional error is around of 0.1 kilocalorie per mole, which is very low, and further developments were also carried out. First, we checked the size of the grid required for these calculations using the well-known Treutler-Ulrichs numerical quadratures, and we found that the smallest grid, which is smaller by a factor of 10 compared to the largest grid, is highly sufficient for these calculations. Moreover, we developed the pre-screening techniques to narrow down the grid to the local domains. In this case, we concluded that around 7,000 to 8,000 grid points per domain is enough, which is pretty low. In general, for DFT calculations, we use a few thousands of grid points per atom. And moreover, the local density fitting approximation is extended and utilized for the CAPS calculation. In this case, we found that around 7 to 8 atoms per domain are sufficient. And a few slides about the numerical results and the performance. We calculated barrier heights for two kind of difficult reaction. One of them was a halocyclization, and the other one was a Michael addition. And these values were compared to good quality CBS references. And as we can see, using double zeta basis sets with the corrections, the error dropped nearly to 0, while significant improvements can be realized for the triple zeta basis sets too. Only one drawback can be mentioned, that here the errors do not decrease monotonically with increasing basis set size, but the performance is still impressive. We calculated the isomerization energy for the ISOL 4 system. The results are very similar. The error drops to nearly 0 kilocalorie per mole with the double zeta basis sets, while while good results are obtained for the triple zeta basis sets too. And about the timings, we measured the additional Wall clock time required for the corrections, and we can conclude that neither the CAPS correction nor the density-based basis set correction are not the bottleneck in these calculations. Of course, the overhead depends on the structure of the molecules and the dimensions of the local domains, but still the overhead are quite favorable. And last, the big guy, counterpoise corrected interaction energy was calculated for a lipid transfer protein system, including more than 1,000 of atoms. And in this case, the error drops from 2.6 to 0.7 kilocalorie per mole using double zeta basis sets, while the time required for the post-Hartree Fox steps was less than a week, demonstrating that this approach can be routinely applied for such big and extended systems. I would like to thank to my colleague and the funding agencies for their support, and thank you very much for your kind attention.
Thank you very much, David. Is there any questions?
So for this protein, how did you obtain the geometry? Is it like some database or?
I think it was from X-ray crystallography, so we didn't optimize the geometry.
Any other questions? No? Okay, then let's thank again our speaker.